Now we come to another major breakpoint, which is we've assembled all of the shortcuts, tricks, techniques in order to get more useful results with less work for design-oriented analysis, where the objective is to get analytic answers that you can put to work. What we're going to do from now on is put them to work, because the rest of the time we're going to take up talking about feedback systems. So feedback systems have some important and not so trivial properties of themselves, which mostly you know about already. But this is the payoff for all the techniques that we've been working at already. Because the problem of feedback system suddenly becomes quite a bit more complicated than the simple amplifier stages. And this is the payoff for the techniques, is to see how you use those techniques to break down complicated problems into the simpler pieces, as we've done already. So this is where we start putting together now several of these little techniques that we've talked about separately. So, starting on the feedback property, here's the basic single loop block diagram that everyone's familiar with. Forward path A, feedback path K, summing junction, and I've generalized the notation again, called the input signal U sub I, because I don't want to say whether it's a voltage or a current, or it may be mechanical torque or whatever. Same with the output. It's an output signal, UO, whatever its nature may be. There's one more parameter, epsilon, which is the error signal. The standard algebra that goes with this is you want to solve for the closed loop gain, the gain of the system in the presence of the feedback, which I'm designating as G. And what you do is you write two equations. One equation says the error signal is the difference between the input signal and the fed back signal, which is KUO. The other equation is the output signal is A times the error signal. Then you solve those two equations simultaneously by eliminating the error signal, which gives you an expression with the output on both sides. And you collect those two terms together and solve. And the result is the closed loop gain is the open loop gain divided by 1 plus AK. And that's the standard result that everyone remembers, even if you know it in terms of different symbols. And already I don't really care for that derivation very much, because it doesn't give you the physical insight as to how the system arrived at that result. So I'd rather look at it in the time domain rather than the frequency domain. So let's start over. Let's imagine the system is quiescent to begin with. Everything is zero. Then at time t equals 0, we come along and we apply a step to the input. That's the green line. What does the system do? Well, first, every practical system has finite bandwidth, which if you translate that into the time domain means that it does not respond instantaneously to a change of input. Therefore, since before the step arrived, the output was 0, then immediately after the step arrives, the output is still 0. Which means that initially there is no fed back signal. So there's nothing to subtract from the input step. So the entire input step hits the front end of the amplifier. That's the red line. That's the error signal. So the initial value of the error signal is equal to the applied step. Now that jolts the amplifier into noticing that something happened. So the output begins to rise from the zero initial value. So the fed-back signal begins to rise as well and begins to subtract from the original step, so the error signal decreases. So during this transient, you have the situation where the output is rising at the same time that the input is falling. The opposite of what you expect in steady state. And in fact, of course, what the system is doing is it is searching for the steady state solution from initial conditions that were not steady state. So what happens is, as the output rises, it subtracts more and more from the error signal, and the rate of decrease of the error signal gets less, and the rate of rise of the output signal gets less as it approaches the steady state simultaneous solution of the two equations. And the final steady state is not zero error signal, but the value of error signal which, when amplified and fed back and subtracted from the input, gives rise to the same value that it started with. That's steady state because it doesn't have to readjust anymore. And so you can label the final asymptotes with the steady state solution, which is that the error signal is equal to the input signal divided by 1 plus AK, and the fed back signal is basically the input signal minus that. Now, it's a little more useful to have this physical interpretation when you think of some typical numbers that may be involved in this. Suppose the forward amplifier is an IC chip. It's got loads of gain, 90 dB, 100 dB, 110 dB, lots and lots of gain. The maximum dynamic range of the output is limited by the power supply, plus or minus 15 volts maybe, or in your case plus or minus 1.5 volts perhaps. Whatever it is, it's limited. Now, when you close the feedback loop around it, the closed loop gain may be only 10, maybe even less than that. 10's typical number. Therefore, to drive the output to full scale, plus or minus 15 volts, closed loop, requires an input of plus or minus 1.5 volts. But if you apply that 1.5 volts as an initial step, to begin with, there is no feedback. The forward path has a huge gain of 100 dB, which is 10 to the fifth. Multiply 10 to the fifth by 1.5 volts, and you do not get 150,000 volts coming out. Because what happens is something hits the stops. Something saturates, shuts off, and the output clamps until the system recovers, which is determined by totally different parameters, such as slew rate, which is to do with what current sources and sinks are available to adjust the internal capacitances to the new values. The problem is totally different. It's no longer a linear circuit problem, with the consequence that these nice, neat, simple waveforms simply don't apply. What happens, of course, is the problem will divide down into a sequence of linear problems as one stage after another comes out of saturation or cutoff and recovers from the overload. The net result, of course, is the transient won't be a single exponential. It'll be a sequence of totally different solutions, probably mostly linear, because of current sources feeding into capacitors. One thing is for certain about it, it'll take a lot longer to reach the final steady state than if the system had remained linear. So that's something to watch out for, especially with modern ICs that have all this gain. That's very nice to have all the gain, but it's also very easy to overload them. when you look into that problem a little more carefully, you find that what really matters is the rise time of the input step, which is not going to be instantaneous anyway. What matters is the rise time relative to the slew rate, to make sure you don't go into an overload if that's a particular concern. But again, the way to tackle those problems is to break down the analysis into smaller pieces. Whenever you can break down one problem into little bits, you have a much better chance of getting simpler solutions that you can then fit together and get more useful information out of it. Anyway, I think that's worthwhile just to talk about the time domain response instead of just the frequency domain response, just because of the insight it gives you into the limitations of the model that you're talking about. So let's go now to representations of the feedback expression. And in this picture, I've just written a whole bunch of names because we don't always have consistency about terminology. The A is the amplifier we start with. I like to call it the forward gain, but sometimes it's called internal gain or the open loop gain. K is the feedback ratio, feedback factor. G is the closed loop gain. But the product AK comes up so many times. Here it is already in the very first line. It has a symbol of its own, T. And I like to call it loop gain because that's the direct physical interpretation. If you start at an arbitrary point in the loop and follow the signal around to the other side of the same point, then you have to go through the product of those two boxes, and so that's the gain back to the same point, which is the reason why it's also called return ratio. The ratio of the signal that returns to a certain point in the loop to the signal that starts out at that point. 1 plus T comes up so often that it also has a symbol of its own. F, I like to call it the feedback factor, because it's the factor by which the open loop gain is reduced in order to give you the closed loop gain. In other words, it's a measure of how much feedback you have. Another word would be the gain reduction factor due to feedback. Another term is return difference. And you might say, since F is 1 plus T, why isn't it return sum? Well, it's a matter of choice of original polarity definitions. Back here in the original picture, I defined these quantities, the error signal in particular, as epsilon is the input signal minus the feedback signal. In other words, I've actually defined this junction as a differencing junction, not a summing junction, by making the minus explicit. So when I follow the algebra through, I get a 1 plus T in the result. Now, we want the feedback to be negative, and the negative is embodied in this minus sign. Because when we get the answer, we want AK, or T, to be a positive number. Numerically, we want to add it to 1. That's what constitutes negative feedback. Which means that A and K have to have the same sign. In other words, they're both non-inverting amplifiers, or they are both inverting amplifiers. And that's the necessary polarity for feedback to be negative. Now, I could have started the other way and put a plus sign here and called that a summing junction. And I go through the algebra, I would end up with 1 minus AK. But I still want the feedback to be negative. So I would have to say in that case that t itself has to be a negative quantity, because I still have to end up adding 1 to the number for t. In other words, I would have one explicit minus sign and another implicit minus sign, which means one or the other of the two boxes has to be inverting and the other one non-inverting. Now, either way is correct, but I just prefer to have the minus signs explicit wherever possible. So I like to have this minus sign explicit in the first place, which gives me a 1 plus t, and I want t to be a positive quantity. I guess the reason for return difference is because Bode, who was one of the first people to deal with all this, he chose it the other way. He wrote his answer 1 minus t. That's okay. That's where the term comes from. Well, we've established the groundwork now. At this point, I usually like to make a little diversion, tell you a little story, sort of background. Negative feedback is usually attributed to Harold Black. Now, Black, of course, didn't invent negative feedback. Nature did that billions of years ago. But Black is credited with the invention of electronic feedback in a usable form. A while ago, in fact, 1977, Black wrote an article for the IEEE Spectrum, and it was probably on the occasion of his retirement. I don't remember which. Anyway, he wrote an article, and it was a kind of historical perspective and narrative and on the early years and how it all happened. And what he says in the article is that in the 1920s, he was a young engineer at the Bell system. And the big problem facing the system at that time was how to design a transcontinental telephone system. And Black was put to work on that, as being the new junior engineer. And you have to remember that at that time, the active devices they had to work with were kind of primitive. Vacuum tubes, that's the only active device there was. And the vacuum tube was pretty lousy. It was lousy in two ways. It was nonlinear, and it was also very variable. Had big tolerances. Now, vacuum tubes are sort of forgotten objects nowadays, and maybe some of you don't even know how they work, but the properties are very similar to transistors, externally at least. Interestingly enough, all of the active devices are nonlinear, including transistors as well as vacuum tubes. In fact, the vacuum tube is probably the best of the lot in terms of linearity, because in a vacuum tube the anode current is a 3/2 power law of the grid voltage. 3/2 isn't much worse than 1, which means the nonlinearity isn't that bad. The next worst is the field effect transistor, the MOSFET. That's square law. So it's that much worse than the vacuum tube. The bipolar transistor is the worst of the lot. That's exponential. So it's sort of interesting to classify them on that basis. But anyway, the other problem with the vacuum tube was equally, if not more, severe. The vacuum tube originally started with a tungsten filament that was heated to very high temperature in order to emit electrons into the vacuum so you could do something with them. Tungsten was chosen because it would stand the high temperatures. But the emission of electrons from the surface of a metal is an exponential function not only of temperature, but of the work function of the material. The work function being the amount of energy necessary to get an electron from the inside to the outside. Tungsten, unfortunately, had a fairly high work function, so it needed a correspondingly high temperature to get any significant emission. But the fact that the emission is an exponential function of temperature means it's highly sensitive to temperature. And the temperature, in turn, is highly sensitive to a lot of things, including the ambient, but mostly to the voltage of the battery or the AC supply that heats the filament. And in those days, they didn't use regulated power supplies for the filaments. So there was a cascaded effect of very sensitive properties. The result being that the electron emission inside the vacuum tube was highly variable. On top of that, of course, is the geometry of the tube itself, which means that the final output current has got additional layers of variation on it over and above the amount of emission of electrons that you get. The net result is the tolerances on the properties of the vacuum tube are very wide. Now, when you consider how you're going to use that to design a transcontinental telephone system, it's obvious to begin with that you've got lots of attenuation in the transmission line, and you're going to need lots of repeater amplifiers along the way, every few kilometers, as a matter of fact. That means that if you put a signal in at one end and you expect to get anything remotely recognizable out the other end, with hundreds of amplifiers in cascade, each amplifier is going to have very tight tolerances on both linearity and gain variation. Now, Black was put to work on this problem, and he recognized immediately this was a losing game. The disparity between the properties of the tube that were available with respect to what was needed in order to put hundreds of amplifiers in cascade was so great that it was a hopeless job trying to make a good enough vacuum tube. And he said this, but he was the new guy and no one listened. So the managers of the time told the engineers, keep on working. So Black did what he was told, and then the next thing he says in his article is he went in to Manhattan Island one evening to listen to a public lecture by Charles Steinmetz. Steinmetz was the electrical engineering guru of the day. He was the biggie. It's interesting also that in those days the public went to listen to scientific lectures. So Black went to hear Steinmetz, and then he says in his article something which I as a professor find very telling. He says he has no recollection of what Steinmetz was talking about. I know how he feels. Yeah. But the reason he mentions it is that something that Steinmetz said put him on the track to solving his own problem. And what Steinmetz was talking about was, if you're trying to solve a problem and you come up against a brick wall and you can't break that wall down, there's only one way to get to the other side, around the edge or over the top. You've got to accept the wall as it is. Now, that was the key. So regardless of what Steinmetz was applying it to, Black started thinking about that approach with respect to his own problem. So sometime later, and I forget how much later it was, he says he's coming in to work on the Lackawanna ferry boat one morning, and he is struck with the proverbial flash of light, the brilliant idea. So he got off the ferry and went into the lab and put his idea together, and this is what he hooked up. Here's the input signal the nice, clean, proverbial sine wave that we all start with. We want to amplify it. So we go through an amplifier with a gain of A made out of lousy vacuum tubes. And what comes out is an amplified fundamental plus harmonics coming from the nonlinearity or the distortion. So he says, let's take that output and we'll attenuate the output by the same factor that we just amplified it, 1 over A. Then let's subtract that from the original input. So what we have at this point is we've attenuated the fundamental back to the same level it had to begin with, so it cancels out. And what we're left with is attenuated harmonics. Now we'll amplify the attenuated harmonics by the same factor again. So we now have harmonics of the same amplitude that we had to begin with, and we'll subtract those out, leaving the amplified fundamental and no harmonics, which is the objective. So we've now eliminated the distortion of the amplifier. We've now made it act as though it were linear, even though it's really not. So that's getting around the side of the brick wall. The tube's still lousy, but we've overcome its consequence. So he hooked it together on the bench and tweaked everything up, and it worked. Great. So he spent the rest of the day writing it up in his notebook, went back home that night, left it running, came in again the next morning, disaster. All the distortion was back again. Well, it's pretty easy for us to see what it was that went wrong. It didn't take him long to figure it out either. He'd solved the problem of distortion of the vacuum tube, but that was only one of the two defects. The other defect was gain variation. He hadn't solved that one. Because what had happened was that the principle of his distortion cancellation was the subtraction of two equal quantities to give 0. Trouble is, you don't get 0 because you can't maintain the tracking. Because of the gain variation, the matching of the paths is not maintained. And it doesn't take much offset to get the distortion almost back up to where it was to begin with. It's the small difference of large numbers problem. Again, not once but twice in the same system. He's trying to do 2 subtractions. No wonder it didn't stay put very long. So, back to the drawing boards. But notice, all was not lost, because he had not wasted the effort of coming up with this solution that didn't work, because it partially worked. It's just like that design, analyze, measure, iteration cycle we have in the design process. You have an idea and you try it out. You make a measurement, and some of it agrees with the prediction and some of it doesn't. So you have to go back and you have to iterate the solution. And you try to find out first what was wrong, second, how might you fix it. So it was not a waste of time coming up with this solution that didn't work, because it partly worked. And as soon as he understood what was still wrong, he was able to figure out what to do about that. So he says in the article he's coming in to work on the ferry again later on, and has the second flash of brilliance. And he never says what it is about ferries that leads to these brilliant ideas, but anyway, this is where he got the second intuitive idea. So he went back into the lab, looked at what he'd done before, and he says the first part of this was okay. Feeding the output back to the input was a good idea. The problem was I tried to amplify the small difference in a parallel path and tried to match the gains with the first path, and that's why it didn't work. So what I'll do instead is I'll just amplify it in the same path. And the beauty of that solution, which of course is what we now know as the answer, the beauty of it is it's self-adjusting. And you don't have to maintain tracking between two paths because there aren't two paths. And the way it works now is, from the point of view of distortion, and I'm sure you've all thought this through yourselves, because when you first learned about feedback, you probably wondered how this happened. And when you think it through, this is what happens. You start with your clean sine wave signal, it gets amplified, and you get distortion products in the output. You attenuate them, subtract them from the input, but there aren't any distortion frequencies in the input, so when you subtract distortion frequencies, they come through in the error signal with reversed phase. Small, because they're attenuated. So the amplifier now has an input that contains attenuated reversed phase harmonics. So it amplifies the reversed phased harmonics, so the new distortion that comes in is partially cancelled, because the phase is opposite. And so in the output, you don't get the ideal perfect result of no distortion, but you get a much reduced distortion. And it's self-adjusting, because whatever is not cancelled out gets to be fed back and re-amplified. It's the reversal of phase that causes the partial cancellation. So he had to iterate the solution to his problem to get the answer that finally worked. That wasn't the end of his article. Because then he says he was sure this was the proper solution, so he told his supervisors the Bell system. They said, "Oh, we tried that before, it always oscillates." Well, Black was convinced that he could make it work anyway, so he continued to prepare patent application. It took him 4 years to get the issued patent. Those days, that was a mighty long time, even if it isn't so long now. And the reason it took so long is that the patent office thought he had a perpetual motion machine. Well, you know, you feed the output back to the input and it makes itself go. Yeah. So they made him take in a working model before they'd process it. Anyway, of course, eventually it worked out, and eventually his supervisors were converted. And so this is what we now know as electronic negative feedback, and is what basically made the transcontinental telephone system workable. However, Black was not a theoretician. He was a nuts and bolts, knob twiddler kind of guy, and admitted it. And he recognized that there were stability problems, but he wasn't the one who pursued that work. But by coincidence, in the Bell system at the same time was Hendrik Bodde. And he was a theoretician. In fact, he was a mathematician. And at the time Black was coming up with his feedback ideas, Bodde was already well launched on developing generalized network analysis methods. And he developed a whole lot of basic theorems to do with network analysis. And he taught in-house courses at the Bell system and developed notes all through World War II. And at the end of World War II, he published those notes in his famous book, Network Analysis and Feedback Amplifier Design. Because when he was part way along doing the network analysis stuff, and it turns out, interestingly, that one of his main objectives in doing the network analysis was to demonstrate that nodal analysis was preferable to loop analysis. I don't think much of either one of them, but as you can see. But anyway, when he heard about feedback, he immediately incorporated feedback into his methods, which is where the second part of the title came from. And so when the book was published in 1945, it became and has remained pretty much the Bible for anyone working with negative feedback. In other words, there's about everything you ever wanted to know about feedback in that book. The trouble is, it's pretty hard to find it. Not the book. The book's easy to find. But looking in the book, it's hard to find what you need from a design point of view. There's a couple of reasons for that. Open the book at random. This is what one of the pages might look like. And here's some equations. And you see it's got all these deltas with subscripts on them, which are determinants and cofactors. And that's natural because his whole basis of analysis is loop analysis and node analysis, which means you solve simultaneous equations, which means that you get answers which are fractions, which are ratios of products, sums of products of all the circuit elements, which is what these determinants are. So no wonder the answer comes out in that form. The trouble with that is it's very high entropy, because it doesn't tell you anything by looking at it. This one here is especially wonderful. You can't even see it. But it's delta prime times delta prime sub 1322 equals, amazingly, delta prime sub 13 times delta prime sub 22. Great. Who cares? You know? And the book is full of stuff like that. These are the answers. So that's one reason why it's very hard to find useful design things in Bodhi's book. There's another reason as well, which is that, you know, in spite of the fact that Bodhi was a mathematician, he did have quite a lot of practical examples in the book. And if you turn randomly to another page, this is what the practical examples look like. Vacuum tubes, of course, and lots of passive elements and lots of magnetics. Remember, in those days, the vacuum tube is the lousy thing, and you don't want to use any more of them than necessary. So certainly not more than 3. And since all of this is to go into repeater amplifiers for transmission lines that require matched impedances, what better way to do it than with a whole lot of transformers? So that's why the examples are mostly of this type. And this was fine at the time, but of course we just don't design systems this way anymore. The whole philosophy is different. Because then you wanted to use as few active devices as possible, but you could use all the passive elements you wanted, including magnetics. Now the philosophy is exactly the opposite. You have ICs with gain coming out your ears. And you don't want anything outside the IC. And what you can put inside is R's and C's, and you can't put inside the magnetics, so you don't want to use them. So the whole philosophy is backwards. So the examples are not very helpful. So, unfortunately, when you go back to look at Bodhi's work, about all that remains of Bodhi is T and F. Those were his symbols, and in the rest of the stuff I'm going to talk about, you won't see any more determinants. Okay, picking up the story where we were with the basic expression for the feedback system. Closed loop gain is open loop gain divided by the feedback factor, F, which is 1 plus T. Now we get to the point where, as I was saying in the introduction, this familiar form really isn't the most useful form. especially with regard to electronic circuits, because the usual approach to analyzing the feedback system is to calculate A and K separately and put them into this equation and find the G. And that's not easy to do, because in order to find A and K separately, you break the loop. And the problem with doing that is that when you break the loop, you actually change the values of A and K, because in most practical electronic circuits, there is an interaction between the two. In other words, this nice, simple block diagram is an oversimplification, because the two boxes are really not separable like that. If they are, it's easy, which in very many mechanical systems is true. You have a mechanical plant, and you have some sort of sensor which provides negligible loading on the output, and the fed back signal is subtracted from the input in a separate device which doesn't interact with the front end of the plant either. So in that case, the block diagram is realistic. But in many electronic circuits, it's not realistic because of interaction between the two boxes at both ends. And so that means that when you represent the closed loop gain in terms of the values of those two boxes, right away you're behind the game, because it's hard to break the loop in such a way as to cancel, as to avoid that upsetting the interaction. So that's a basic problem with the conventional approach. And so I'm suggesting an alternative approach, which is potentially beneficial, because not only is the A, for example, difficult to calculate directly itself by breaking the loop, but it isn't part of the answer that you're interested in anyway. The G is the thing that has to meet the specifications. That's what the ultimate outcome has to be, is the G. You as a designer are concerned about how you're going to get it, but someone else as a customer couldn't care less how you get it. He's going to buy the result, not the method. So if it's not only difficult to calculate A, and also you don't really care what it is in the end anyway, wouldn't it be better to have a formulation of the system basic equation which avoids specifying what A is? So it takes a very simple step to do that. All you do is take the original expression and you multiply top and bottom by K. So now you have AK over 1 plus AK, and AK is T. So the A has disappeared. I shouldn't really say it's disappeared, but it's become hidden. It's only inside the T. But it means we don't need to know what A is by itself. T is the quantity we need to know, because that's what the answer is expressed in terms of. And this is a much more useful version of the result anyway, because we can identify these two separate factors which have direct physical interpretation. In particular, the 1 over K in front is the limiting value that the closed loop gain is going to reach if the loop gain approached infinity. So it's a reasonable expectation that if feedback is going to be any use at all, the more you have of it, the better. Which means infinite T is the ideal limit. And so if you could make an amplifier with infinite T, its closed loop gain would approach 1 over K. So why don't we change the symbol? Because if G is going to approach this value, why don't we give it a symbol related to gain? So we'll call it a G, and we'll put a subscript on it as a reminder that this is a limit achieved if the T goes to infinity. Another useful thing about that quantity is that it's the only thing that we know when we start the design, because it's the specification. So it's what we're aiming for. And since the design problem is how to overcome this terrible disadvantage of having a huge number of unknowns and hardly any equations at all, certainly it's going to be helpful if we get the one thing that we do know into the expression for the result that we want to get. So for both of those reasons, the G infinity is a useful quantity. Well, what's left behind is the other quantity, which I've given a symbol of its own also. That's D. D stands for discrepancy factor, for obvious physical reasons. It's the discrepancy between the ideal limit, the specification, and what you're actually going to get. The objective is to make D as close to 1 as you can, which is what happens as t approaches infinity. Now, it's pretty easy to make D arbitrarily close to 1 by making t large enough, which is very easy to do, especially nowadays, because we have the ICs with umpteen dBs of gain. So that's easier than it used to be in Black's time, where you had to work with a minimum number of tubes that didn't have much gain anyway. So that's easy, but the hard part of it is the frequency response. Because t is going to go to 0 eventually at infinite frequency, regardless of what else you do. So no matter how big you make it at lower frequencies, ultimately t goes to 0, which means somewhere in between it crosses unity. And where t crosses unity is about where the d starts to fall off. See, if t is 10, d is 0.9. So it's still pretty close to 1. If t is 1, t over 1 plus t is already 0.5. And you're starting to deviate significantly from the ideal limit. And ultimately d goes to 0 as t does. So the hard part of designing a feedback amplifier resides in only one of the three requirements. The first requirement is you make G infinity what it needs to be, which means you design the feedback path independently to get the required G infinity. That's easy. The second requirement is you make T very big. That's easy. The only hard part is making T big over a wide enough frequency range. As I mentioned in the introduction, you're certain to have a problem at the high frequency end because T will always go to 0. You may have the same problem at the low frequency end because if the amplifier is AC coupled, then T is going to go to 0 at 0 frequency as well. But we're well prepared to deal with that now because we've already established the symmetry between the two directions of the frequency axis, which involves a horizontal reversal of all the diagrams to do with sketching the asymptotes, and it consists of simply inverting the frequency variable. Wherever you have an S for high frequencies, you have a 1 over S for low frequencies. So we've already set up the mechanism to deal with this problem at low frequencies once we know how to deal with it at high frequencies. It's just a symmetrical situation. So I'm proposing now to deal with the whole subject of analysis and design of feedback amplifiers using this representation. In other words, we've substituted the quantities that are of importance in the result into the original expression. And the important quantities are the specification, G infinity, and how close you're going to get to it, which in turn is directly related to the loop gain. And those are basically the only quantities that you really care about in the feedback system. Because if the answer is expressed entirely in terms of those two quantities, then that's all you need to know. And the A has, if not vanished, at least it's been relegated to a position of much less significance. Now, the G infinity may be a new symbol to you, but it's really pretty close to something that's very familiar. So I want to take a moment to describe that. Here's one of the two typical configurations of an operation, a feedback amplifier, built around an IC chip, like the generic 741 or whatever the latest generation may be. It's got lots of gain with a differential input. A very common connection to feedback is you take an impedance divider, which is the K box. So K is ZA over ZA plus ZB. So the fraction K of V2 is fed back to the input. This is a standard configuration. How do you go about calculating the gain of that amplifier? You do this all the time. Well, the usual thing that happens is you make the assumption that the A box is infinitely large gain, which is a pretty good approximation, isn't it? And the reason you do that is that whatever the output voltage is within its dynamic range, if the gain A is large enough, the error signal or the differential signal at the front end becomes vanishingly small. Whatever the output is, it takes a vanishingly small input to get it, the larger gain you have in the forward path. And if the error signal is vanishingly small, what it allows you to say is that VA approximately equals VB. But VA is equal to the V1 input voltage and VB is equal to the fed back voltage. And so if you're allowed to say that they're equal, it says KV2 equals V1, so V2 over V1, which is the gain, is 1 over K, which is the reciprocal of the feedback divider. And that's the usual approach to calculating the gain of the feedback system. Now the thing I want to emphasize about this is what you have calculated is really G infinity. Because to get that answer, you made the assumption that the A was infinitely high, which is the same thing as assuming that the loop gain is infinitely high, which in the new notation is the same thing as saying D is 1, G equals G infinity. So this is how you calculate G infinity. But the important thing to remember is it is G infinity that you've got and not G. Because in actuality, the forward amplifier gain is not infinite. And it may be huge at a very low frequency, but it's also got a low frequency pole in it. Which means at some higher frequency, the gain certainly drops off, and in fact it eventually goes away. Which means that the assumption that you've used to calculate this result breaks down. Which means that the actual closed loop gain is no longer equal to this ideal G infinity. That's the other part of the problem, the D part. And it's the part that usually gets neglected in the design of the system. Because everyone does the part with G infinity, forgetting that it's G infinity and not G, and forgetting to do anything about the D. But you see, ultimately you have to, because D goes away at some high enough frequency. So this is simply a way of emphasizing the fact that the G infinity really is not a brand new quantity. It's the quantity you previously called the gain of the system, and the only modification needed to that is that it's the ideal limiting gain of the system if you had infinite loop gain. Exactly the same thing is true for the other standard configuration of feedback. Again, the feedback is returned to the inverting input. This is actually the dual of the other one. And the standard way of calculating the closed loop gain of this system is, again, you make the assumption that the A is infinitely large, which allows you to say the error signal is 0, which in turn allows you to say that the error current into the amplifier is 0, which allows you to say IB equals IA. But IA is V1 over ZA, because the right-hand end of ZA is at AC ground, because of the 0 error signal. And IB is equal to V2 over ZB, again because of the virtual ground at the end of ZB. So IB equals IA, or V2 over ZB equals V1 over ZA, so V2 over V1 is ZB over ZA. And that's what most people consider to be the gain of this configuration. But once again, what you really calculated is G infinity, because it embodies this assumption of infinitely large gain of the forward path. So it again neglects the fact that there is a D factor, which comes in when the amplifier gain drops off at higher frequencies. So the same result. What you've calculated is really G infinity, and you oughtn't to forget the other part of it, which is that the T and the D ultimately will go away, and the actual closed loop gain will cease to be equal to this ideal value. One little side point about this, which we'll come back to later on. If you assume infinite gain of the forward path, this says that the error signal is vanishingly small, which says that the error current is also vanishingly small. And that requires no assumption to do with the input impedance. If you've got 0 voltage, you're going to get 0 current, even if the impedance is only 1 ohm. So it's important to notice that no restriction is implied in this result to do with whether the input impedance is high or not. Okay, that sort of linked this new notation with G infinity to what you've done before. It turns out that it's only part of the solution and not all of it. You still have to worry about the T. Okay, let's go on now and look at some of the consequences of these interrelationships, again for the purpose of keeping the qualitative interpretation in the front of our minds. So we don't simply rely on the mathematics and the algebra. Because once you let go of the physical significance, that's when you start getting into trouble. Okay, so let's look at some of the interrelationships between these various quantities. Let's start with the specification, the G infinity. The vertical axis is various gains in dB as usual. So I've drawn G infinity, the specification, at some arbitrary level. If I'm going to build a feedback amplifier that's going to have a closed loop gain which is close to G infinity, then I better start with a forward amplifier that has a lot more gain than that, because I know feedback is going to lower it. So I better start out with some spare. So I'll start with an A which is bigger than the G infinity. And the result of that is I'm going to end up with an actual closed loop gain that's going to be a little bit less than the G infinity. Now the geometric relationships between those quantities are T is A times K. But K is 1 over G infinity. So T is A over G infinity, which is a ratio. But on the dB axis, that means T is equal to the dB difference between A and G infinity. So on the dB graph, the number of dB between the A line and the G infinity line is the value of T in dB. And for the same reason, the number of dB between the A line and the G line is F in dB, because F is the ratio of A to G. What is the number of dB between the red line and the green line? What quantity does that represent in dB? Yeah, D, the discrepancy factor. This additional parameter that you have to worry about all the time. D is the discrepancy between G infinity and G. And in dB, it's the vertical displacement on the dB axis between those two quantities. And I'm glad you got that, because the tendency is to say the difference is 1 by looking at these other two quantities. But of course that's not correct, because the 1 is an additive term to the T, not a multiplier. So the difference between the red and the green line in dB is the discrepancy factor D, and as D approaches 1, the green line approaches the red line, because dB goes to 0 as the ratio goes to 1. And the other picture is what happens if you have the same specification, but you started out with a forward amplifier that had a bigger value of gain A. Both the T and the F get bigger, and the D gets closer to 1. And ultimately, if the A went to infinity off the picture, D would go to 1 and G would approach the G infinity. So the purpose of this is to give you a little physical intuition as to the relationships between these quantities. Here's another basic property of feedback. It's commonly said that feedback reduces the sensitivity of the closed-loop gain to variations in the internal parameters. That is, if you have a certain tolerance on a component, say 10%, you put a feedback loop around it, you will get less than the 10% variation in the resulting gain. That's one of the important reasons for using feedback. So that's a common statement. Feedback reduces sensitivity to the variations of the internal components. That's only partially true. What feedback really does is it transfers the sensitivity of the closed-loop gain from components in the A box to components in the K box. It doesn't get rid of it, it transfers it. And it's easy to see why by looking at the limiting cases. If the T goes to 0, G approaches A. That means you have no feedback. So any variation of the A parameter shows up 100% in G. If you go to the other extreme, G approaches G infinity, which is 1 over K when T goes to infinity. So variations in K show up 100% in G. That's complete transfer from one extreme to the other. And the intermediate case is easy to find also. Here's the general relationship. G is a function of A. Take logs of both sides, differentiate, collect the terms on the right, and the result says that the fractional variation of G, that is percentage variation, is made up of contributions from the percentage variation of components in the A box and percentage variation of components in the K box. And the contributions are weighted differently. The A contributions are weighted by 1 over 1 plus T, which means that the bigger T is, the smaller the weighting factor, and the less important variations of A become. But the K parameters are weighted by T over 1 plus T, and that goes the other way. The bigger T is, the more important variations of K become. And of course you end up with the two extremes. So this is the quantitative relationship for any intermediate case, showing the relative importance of the variations of components in the two boxes in determining the resulting variation of the closed loop gain. Something very fortunate happened in that, because the main reason that Black introduced negative feedback or began to think about the idea was to overcome the lousy properties of the vacuum tube. Two of them, nonlinearity and gain variation. And feedback helped a lot. But the reason it helps is not because feedback simply reduces the effect of the A on the closed loop gain. It transfers the sensitivity to components in the feedback path. But the thing that saves the whole problem is that the feedback path doesn't have any lousy vacuum tubes in it. If it did, you wouldn't be any better off. And the reason you don't have vacuum tubes or any other active device in the feedback path is that you're trying to build an amplifier with a G infinity bigger than 1, but G infinity is 1 over K, so K is less than 1. So K is a passive attenuator, and it doesn't need active devices. And it's because the passive devices are much more ideal components than the active devices are. They're more linear, they're more stable. That's why feedback gives you benefits. So we sort of lucked out that you don't need active devices in the feedback path. It isn't often you find anything that's counter to Murphy's law. Okay, let's go on to something a little more important. The effect of feedback on the bandwidth of the amplifier. Let's take the simplest possible frequency response of the amplifier in the forward path, which is a single pole. You can't have any less than that. We've already seen, because every amplifier's gain is going to go to 0 at infinite frequency. It has to have at least one pole. So let's represent that simplest case. A midband value AM and a pole at omega 1. What is the closed loop gain G? Well, it's a simple algebraic substitution into A over 1 plus AK. Let's assume for the moment the K is flat. It doesn't have any corner frequencies. Of course, this isn't necessary, but let's keep it simple to begin with. So K is simply a constant. So the direct substitution of the A into the formula and rearrangement into the factored pole 0 form gives you this result, namely a flat gain and a single pole. And you identify those flat gains as the coefficient in front is the midband value of the closed loop gain, which is GM, and the pole is the pole in the closed loop gain, which is FM times the pole of the open loop gain. So down below, I've sketched the two gains, the open loop one, which is the blue line, and the closed loop one, which is the green line. And of course, the midband values satisfy the basic relationship. Closed loop midband gain is the open loop midband gain divided by the midband feedback factor. But the important result of this picture is that the pole of the closed loop gain lies on the same asymptote as the pole of the open loop gain. Because the algebra shows that the relationship between the two flat gains and the two corner frequencies satisfies the gain bandwidth trade-off. It's the same ratio. Because the ratio of the midband gains is FM, so is the ratio of the two poles. Therefore, the two poles lie on the same asymptote. So that's a very simple, basic relationship. In other words, feedback gives you the flexibility of actually achieving the gain bandwidth trade-off. You can actually trade gain for bandwidth, 1 for 1, according to how much feedback you use. Notice this is a much better deal nowadays than it used to be, because we can start out with a lot more gain available to be traded with modern ICs. It isn't quite that good, though, because you also start out with a lot less bandwidth, because the pole of a 741 is around 10 hertz. So it's a good thing you got a lot of gain to throw away. This picture does not display a 0 dB axis. It's down here somewhere, probably because you're trying to build a gain bigger than 1. But it isn't of any great significance in this picture. But if you draw a different picture representing the loop gain, T is A times K. So if A has a single pole and K is flat, then T has the same single pole. And if you draw the asymptote sketch for T, you have a mid-band value Tm, a pole at omega 1, and then it drops off. Now this time the 0 dB axis is very important, because it divides the frequency axis into two ranges. The frequency where the T crosses 0 dB obviously is what is identified as the crossover frequency. It's where the magnitude of T equals 0 dB or 1. Below that frequency, T is bigger than 1, which means you're going to get all the nice benefits of feedback. But beyond the crossover frequency, T is less than 1, and you don't have any feedback. It's gone away. You might as well be open loop. So this is the important thing, which is really the same problem as the fact that you have to worry about the D, which is what D goes away. It's why the closed loop gain ceases to follow the open loop, the G infinity. It's because in the same system, you have to deal with the case where you have a lot of feedback and where you don't have any feedback at all in the same system at different parts of the frequency range. So that's why a picture of T, including the 0 dB axis, is a very important picture, because it's what divides the overall response into those two different ranges. Okay, now we're going to start another important little derivation technique. T is the most important fundamental quantity, but there are two derived quantities, F, which is 1 plus T, and D, which is T over F. So we're going to start with T, because that's the thing we're going to calculate directly from the system. And the next objective is to find out the two derived quantities. First, the F. So I'm going to do that graphically on this picture by a procedure which I already used in the example earlier on to do with why a right half plane 0 can show up. Down here, T is large. Now I'm trying to construct F equals 1 plus T, which is adding two functions. One of the functions is only 1, but nevertheless it's a function. Okay, down here T is large, so F is going to be just a shade bigger. So I draw another line down here just a little bit above this one. I label that one Fm for midband value is 1 plus Tm. As T goes around the corner, F will go around the same corner because it's still just a shade bigger than T, as long as T stays large. Now I'll jump to infinite frequency. T has gone away. The only function left is 1, F is 1, which is 0 dB. The only part that I don't know is how to join these two together. Again, this is not an exact geometric construction because you don't add two functions by adding the dB. It's whichever one is larger dominates. Now, as I suggested in the earlier example, what's the simplest possibility? The simplest possibility for the region of interaction is that you can find what happens simply by extrapolating these two asymptotes until they intersect. This is a guess. Not sure yet whether this is right. But remember the basic philosophy. Stick your neck out. Try it and see. Do whatever you can to get an idea of what might happen, and then you go back and clean it up or fix it up later if necessary. But do anything you can to get an answer. So let's go ahead with the guess. If it's right, what is the value of this frequency? Well, gain bandwidth trade-off gives it to you right away. Because down here the magnitude is FM. Down here the magnitude is 1. Here the corner frequency is omega 1. Therefore this corner frequency has the same ratio to omega 1 as this magnitude to 1. So the value of this corner frequency is FM times omega 1. If that's correct. We're still out on the limb. We're still guessing. But go one step even further than that. The things that you practiced earlier on. Given an asymptote sketch, write the factored pole zero form. We have two flat gains. You can choose either one as reference, depending on whether you want the answer to have the zero frequency flat gain as reference or the infinite frequency flat gain as reference. The choice is obvious this time, because the interesting part of the problem is at low frequencies where you have a lot of feedback, so that's clearly the one that you'd want to adopt as reference. So you write it, F equals the low frequency flat value, which is FM, and then you look down and you look up in frequency and see what happens. If you look down, nothing happens. If you look up, you see a concave downwards corner, which is a normal pole at omega 1. You continue to look up, you see a concave upwards corner, so that's a normal 0 at FM times omega 1. That's the answer, quantitative, for the factored pole zero form for F, which has been derived by a geometric construction with no algebra. Well, that's nice, but then you say, well, that involved a guess. We'd better go back and check that. Well, it's easy to check it, because this is a simple case, because it's easy to do the algebra. So, here's 1 plus the t, and the t is Tm with a single pole. Cross multiply gives you 1 plus Tm plus S over omega 1 over 1 plus S over omega 1. Pull out the 1 plus Tm from the numerator. A little sketchy. Well, was the guess correct? Sure. Same result. Fm is 1 plus Tm. So we validated the construction method. Well, okay, you say, well and good, but why bother with the graphical method? Because the algebra was easy anyway. Well, that's true in this example. But the value of the graphical method is that you can still use it when there's a lot more complicated things going on round about. That is, in cases where the algebra is a lot worse. And it's easy to see what the next step would be. Suppose you had an AC coupled system and the loop gain drops off at the bottom end as well. That's another pole. So the formula for T would have two poles. So how do you find F algebraically in that case? You have to cross multiply. You have to multiply the two poles together, add a constant. That gives you a new quadratic to factor. Well, you can handle that all right now if you use the new version of the quadratic, but still it's noticeably more work. The graphical method would remain just as easy. And the next step after that is what happens if T has three poles. Now you get into deep water, algebraically, because you have to cross multiply and refactor a cubic equation now. Even more difficult. Although, as you saw in the introduction, maybe that can be done too, but still requires more effort. The point is, when the T gets more complicated, the algebra rapidly escalates. But the graphical construction will remain simple. That's the value of it. That's why it's worthwhile validating this construction. Because when it gets to real life cases that are much more complicated, the graphical method is probably the only way you'll get an answer. Okay, here's the neat version of that. So this is the first derived quantity. Starting from the T, we have now found F quantitatively in factored pole zero form by using a graphical construction and writing the answer in one line without doing any algebra. The second derived quantity is easier. That's how to find D. D is T over 1 plus T, or T over F. Well, now we have T and F, and this construction is done exactly because we have to compute a ratio, not a sum. A ratio is exactly the difference between the red line and the blue line. So if I subtract the blue line from the red line, then I get a small negative number of dB. And since the blue and the red line have the same pole at omega 1, the orange line doesn't even show it. When I subtract one from the other, the difference is the same. And the difference remains constant until you get to this frequency where the blue line levels off and the red line keeps on going. And so now the orange line simply follows the T because the blue line is at 0. So I can write the answer down directly. This is the midband value for D, which is dm, which is Tm over Fm. I better change over to the black pen. And so the frequency response of the D is D equals dm, the flat value, and it has a single pole at the frequency Fm omega 1. Notice something that we'll be coming back to reconsider later. The pole of D is the same as the 0 of F. So here's the neat version of that. So now we have both of the derived quantities. Starting with T, we have F and we have D. That's all we need now to find the final closed loop gain G, which is G infinity times D. The G infinity is the specification we started with, and in this example we've taken it to be flat with no frequency dependence. We have now found D, which is the orange line. All we have to do is multiply the two functions, which means a direct addition on the dB axis. And the sum of the red line and the orange line is the green line, and that's the final closed loop gain, which is G equals Gm, where the midband Gm is G infinity times Dm, and it has the same corner frequency that the D does. Now, this is the end of the analysis, because we now have identified the midband values and the frequency response of all of the quantities that determine the closed loop gain of the system. And the G infinity we knew to begin with, because that's the specification, and all we started with was the T. I've assumed that we've analyzed for the T. A little later on we'll see how you do that. But having found the T, this is how you pursue the result to the answer. And there's no algebra, simply graphical constructions. And note that the actual closed loop gain that you're going to get, which is the green line Gm, is pretty close to the G infinity, but only up to a certain frequency. And after that, it drops off. That's because the T has gone away, therefore the D has gone away. The discrepancy factor begins to to decrease beyond that frequency. So when you have a specification on your closed loop gain, it also has a spec on the required bandwidth. And that's where you have to put this pole. That pole has to be at least as high as the specification requires. So the point about this is now we're making a little transition between the basic building blocks and the basic techniques which so far we've used only to illustrate very simple problems. But now the problem is getting more complicated, namely dealing with feedback amplifiers. So the important thing to keep a hold of while we do this is to keep the analysis simple. See, this is the point where most people, in making the transition from being a student to a working engineer, this is the point where most people fall off the wagon. You see, because they try to apply the academic techniques to the more complicated problem, which they haven't practiced much before. And they can't do it. They don't have the time, for one thing, to do all their work that it seems to take to get the answer. But more important, they haven't been exposed to this motivation of how to keep the algebra simple. That's the key to getting the answer to complicated problems. The key to it is keeping control of the algebra even though the problem gets more complicated, which is what I said right at the beginning. The name of the game for all of this stuff is not to fight the rearguard action against overwhelming algebra that's always pressing in on you from all sides. You're desperately trying to stay afloat in this ocean of math. The key is to avoid getting into that position. So you keep control of the algebra. So you're swimming in a small pool instead of the ocean. That's why you have to break the problem down into smaller pieces. That's separating the ocean into smaller pools. You've got to do that so you can keep control of it and make the algebra come out the way you want it to. So you can make it tell you what you need to do to use it backwards, which is the nature of design-oriented analysis. And here in this example, this is one of the first ones where you begin to see the value of doing this, where you have all these derived quantities, and you've broken down the properties of the feedback amplifier into two separate factors. That makes it simpler to begin with. And you deal with each factor separately. And even in doing that, you always do as little algebra as possible by doing as much of it as you can on the diagram, which we talked about already. Now we have, for the first time, done the algebra on the graph. That's the latest technique, doing the algebra on the graph. That's why I've emphasized this technique so much, in spite of the fact that it looks so simple, it's hardly even worth talking about. But the point is, this is what saves the day when you get to complicated problems. And it's so important to be aware of this and to practice doing it, that I'm going to arrive at this very same answer by a different path, also graphical. Back to the loop gain we started with, the single pole function. The ultimate objective is to find G, the closed loop gain. So one of the steps along the way is to find D, which is T over 1 plus T. But if I rearrange the expression like this, it changes the algorithm, because the graphical sequence is now different. So I start with T, and the first thing I have to do is find 1 over T. That's a reciprocal. That's a vertical inversion of the logarithmic scale. So 1 over T looks like this. The next thing I have to do is add 1. At low frequencies, 1 over T is very small. So when I add 1, the result will be just a little bit bigger than 1, or just a little bit bigger than 0 dB. And as T begins to increase, it still won't be visible. But it'll become visible when 1 over T overtakes 1. Then the sum of the two will turn around and follow the bigger one. And by gain bandwidth trade-off, the value of that frequency, again, is Fm times omega 1. That's the denominator of D. So to find D, I have to take the reciprocal of that, which is another vertical inversion. So the orange line is the vertical inversion of the green line, and that's D. And of course, that's the same answer we had before. It's just arrived at by a different process. And I did that to emphasize the power of this method, the flexibility you have. But in any case, the algebra is minimal. And yet you still get quantitative answers. That's the important part. You still get the equations, still quantitative, but you just write them down by looking at the picture. So, even though in these simple cases we could have obtained the pole zero forms for F and D by algebra, the graphical procedure saves the algebra in much more complicated cases where it might easily get out of hand. So this is an example of the technique of doing the algebra on the graph, which was one of the techniques in that original list that we had right at the beginning. So notice that using log-log scales for dB versus frequency permits the determination not only of exact products and quotients, because products, quotients convert directly into sums and differences of dB, but now you see how you can also do it to compute sums and differences. A technique that no one emphasizes in the textbooks. Now the next section is to do with one of the other basic properties of feedback, which is reduction of interference signals. So here's our forward amplifier. Input signal UI, output signal UO. And we suppose that there's some interference signal which is introduced partway along the forward path, where I've divided this into two blocks, A1 and A2. If we're going to see what the effect of feedback is on the interference, then of course we ought to establish a reference condition as to what the interference does before we put the feedback around it. So let's identify that in terms of the interference to output transfer function. So for the open loop amplifier, the total output is the linear superposition of A1, A2 times the input plus A2 times the interference. The interference is introduced through a simple summing junction. So the interference to output transfer function is just the A2 box. Now to see what effect feedback has on that, we put the K box around it and close the loop. Now we solve the problem again for the interference to output transfer function. You solve the simultaneous equations as before, but we have an added term now from the I. And when you solve it, you find that the I affects the output with a coefficient of A2 over 1 plus AK. So the interference to output transfer function is the value that it had before feedback, which is A2, divided by the feedback factor. So feedback reduces the interference to output transfer function by the feedback factor, the same factor that the overall signal gain is reduced. The interpretation of the interference signal is where this becomes useful, and it has lots of interpretations. One of them is that the interference may be power supply ripple. It's just another input that comes in part way down the amplifier's string. It may also be thermal noise, which mostly comes in the first stage. It may be distortion, which is represented by a harmonic generator usually developed in the output stage of the system. So the interference is a generalization of a lot of spurious signals that may get into the system. Well, it didn't take very long to go through that. That's a standard result.